Okay, everybody seated comfortably. So, welcome everybody to this 35th Annual Goldschmidt Conference, which is organized by the European Association of Geochemistry and the Geochemical Society. I'm Martin Whitehouse. I'm co-chair of the meeting this year, together with my fellow co-chair, Karen Hudson-Edwards, and I'm also welcoming on the stage Thomas Magner, who is chair of the local organizing committee. We're very happy to welcome you here, whether you're attending this meeting in person or remotely from somewhere around the world. Altogether, we have 4,200 in-person and remote delegates from more than 70 countries, including over 1,300 students. I think this clearly shows the growing impact that geochemistry is having, a discipline that's got remarkably diverse fields, ranging from modern environmental change to planetary evolution. So preparing a meeting like Goldschmidt requires a very large number of dedicated people. Most of them are volunteering their time in support of the field. So to start off, we wish to thank our colleagues of the organizing, science, and early career program committees who've done a tremendous job putting the conference program together, as well as the many scientists who've contributed to this task. To put this into numbers, there are 45 theme chairs, nearly 540 conveners, 81 organizers of 21 science workshops, 200 mentors, 31 panelists of the 14 early career workshops, and 5 conference bloggers. Additionally, there are 46 student helpers and their manager, Eduardo Amanati, they're here in the orange shirts, who are here to help you with everything from finding the right lecture room to finding the right metro station. We also thank the staff of JPDL for providing all the logistics behind the meeting, the staff of the IT company Confex, our press review team, and Campus PR for managing press and media. Further, we acknowledge the support of our exhibitors and sponsors, and we invite you to visit them in the exhibit hall until Thursday. Finally, a very special thanks is reserved for our exceptional EAG staff, Mary Ord and Alice. Without their dedication and enthusiasm, none of this could happen.
We want to make this meeting welcoming, safe, and inclusive for all participants, and we want to encourage open and respectful dialogue. Since 2018, the Geochemical Society and the European Association of Geochemistry have adopted a code of conduct and created the AMIGO program. AMIGO stands for a more inclusive Goldschmidt. Should you experience or witness any inappropriate behavior, you can always report this to the help desk or contact any person, like me, wearing a yellow AMIGO ribbon on their badge. To keep Goldschmidt more accessible and inclusive, the societies continue to provide free remote registration to all participants from low-income countries, and this year have more than doubled the number of grants available. We want to remind you that all presentations are recorded and available for 30 days after the conference. Remote oral presentations and all posters from both in-person and remote presenters can be viewed on the conference website. Don't forget, you can leave questions for the authors or connect with presenters via the website.
Hello everyone. Thanks for coming. In this place, it is our great pleasure to acknowledge several supporting organizations of the entire conference. First of all, we sincerely thank to the City of Prague for the generous support of the Goldschmidt Conference and for releasing free transportation passes for everyone here at the conference. These passes allow you to travel within the Prague using subways, trams, buses, trolleybuses, boat ferries across the Moldau or Vltava River, and also trains within the city limits. Further, we also acknowledge, or we also are grateful to the Prague City Tourism Office, which provided additional support for this event. Also, we are indebted to the entire staff of the Prague Congress Center for their tireless effort in making this event as smooth and convenient as possible for all participants and for the members of the organizing committees in particular during almost 2 years long preparation work. Lastly, we express our gratitude to the Faculty of Science, Charles University in Prague, for hosting these scientific workshops, which we hope have been of notable knowledge transfer to the participants. We hope you will enjoy your stay in Prague.
We thank you again for participating in this Goldschmidt Conference, and we really wish you a wonderful week. The success of this Goldschmidt will be your success too. It is now my pleasure to invite Dan Frost, the President of the European Association of Geochemistry, to come to the podium. Thank you.
Yeah, good morning, everybody. Welcome. I hope you're enjoying Prague and the meeting, of course. So as President of the European Association of Geochemistry, it's my honor to present our awards. And I'd first like to thank everyone who has taken the time to submit a nomination. We also like to appreciate the work that's done. I'd like to say thanks to the work that's done by the EAG Awards Nomination Committee. They put a lot of time and effort in trying to find people and to make sure that our awards are evenly distributed and fairly distributed through the community. I also should say that this year, our council has decided to make it easier to submit an award, in particular for the URI Award, which is our highest honor. We have a new nominations process and a new nominations form that should make it faster for anyone, and I repeat, anyone, to submit a nomination. So please note also that the criteria for making a nomination for the Science Innovation and Houtemans Award has also been modified. So finally, I would note that there's a new submission deadline of the 30th of October, and I really, like I say, I really encourage you all to think about recognizing deserving colleagues who might be sitting next to you right now, for example, or just in front of you. So our first award is the Frederick Houtemans Award, recognizing exceptional contributions made to geochemistry by a member of the younger generation. And this award goes to David Beckert from the University of Lorraine and CRPG. So David developed with colleagues at the Woods Hole Oceanographic Institution the sub-per-mil analysis of noble gases in volcanic gases, leading to unprecedented insights into mantle geodynamics. Thanks to noble gas analysis of lunar material, he demonstrated the contribution of comets to the Earth-Moon system. So unfortunately, David could not be here with us today, but we will recognize him in person in Montreal next year. I should say his wife is expecting a baby, so he's got his priorities in the right place. So our second award is the Science Innovation Award, which this year goes to Christine Putness from the University of Munster. Christine is an influential scientist in the field of fluid rock and fluid mineral interface geochemistry. Specifically, she has shown that interface-coupled reprecipitation is generally how a solid re-equilibrates in the presence of the chemical evolution of the overlying fluid phase. She's also the leading international expert in mineral growth inhibition via various organic moieties, and as well as both mineral dissolution and growth processes via natural and anthropogenic chelators. While Christine has built a highly impactful body of research, equally important is her generosity in helping others in their research endeavors. So please join me in congratulating Christine for her exceptional scientific achievements and her contributions to the scientific community. So our highest honor is the Harold Urey Award, recognizing outstanding contributions to advancing geochemistry over an entire career. That sounds a bit harsh. Okay, the career might continue to a bit, at least, yeah. Okay, so the career's not at an end. Okay, this is midpoint, I should say, yeah. Okay, so the 2024 Urey Award goes to Jana Bliketov from the ENS Lyon. Jana could not be in Chicago last year, so we're very happy to recognize her this year. Jana is a leading light in the study of planetary mantles and crustal evolution on Earth and other solar system bodies. She's helped pioneer both new applications of isotope geochemistry with specialization also in the highly cytophile elements, to name but a few lines of inquiry in her exceptional bibliography. Moreover, her work has helped to steer radiogenic isotope geochemistry more broadly towards quantitative applied chemical geodynamics. Jan is also an unwavering supporter of our community in various fields of geochemistry in Europe and also throughout the world, as exemplified by her generous devotion to supervising students, postdoc scholars, and service to the professional organizations, and also the leadership of journal editorial boards. So please join me in congratulating Jana Bliketov for her outstanding contributions to our science and also to our community. So, and this year's URI Award goes to Donald Sparks from the University of Delaware. Don is a leading scholar in geo and soil chemistry, having contributed widely and deeply to our understanding of reactions at the solid water interface. He was a pioneer of chemical kinetic and spectroscopic techniques for illuminating reactions within soils and sediments. He helped lead the use of X-ray absorption spectroscopy for discerning metal binding and later the chemical characteristics of soil organic matter. While being a prolific and impactful scholar, Donald Sparks' advising and mentoring is possibly even more impressive. He's also a prominent leader in the scientific community, taking leadership roles in several societies. But unfortunately, because of a last-minute unexpected circumstances, he can't make it today, but we also look forward to recognizing Don in person next year in Montreal. So, finally, it is my great honor to now introduce my colleague, Elisabeth Sikes, President of the Geochemical Society and Professor of Oceanography at Rutgers University, who will present the first of our plenary lectures. So, Elisabeth is a paleoceanographer and paleoclimatologist whose interests focus on the influence of the oceans on carbon cycling and climate. So through analysis of carbon and oxygen isotopes and also organic biomarkers generally taken from cores from beneath the ocean's floor, she examines sea surface temperatures in the past and how the CO2 capacity of the oceans has changed not only with time, but also with ocean depth in the past. So Elisabeth studied marine sciences at the University of North Carolina and received her PhD through a joint program between MIT and the Woods Hole Oceanographic Institution. She then started her odyssey in the Southern Ocean, working at the University of Tasmania and the Australian Geological Survey Organisation. She joined the faculty of the University of Auckland before returning to the Institute of Marine and Coastal Sciences at Rutgers University in New Jersey. So what I find personally truly remarkable about Elisabeth's work is that whereas a geologist can simply turn up to a rock outcrop and take some samples and try and prove a hypothesis, Elisabeth is confronted with this vast and still poorly explored ocean floor, where the recovery of samples from beneath the ocean floor is both technically challenging and logistically complex due to the need to then coordinate large-scale ocean research cruises to presumably just the right places. So, and Elisabeth has of course taken part in a very large number of these types of cruises to the polar and subpolar waters, and also on a number of these cruises she's also been the chief scientist. So in addition to her leadership as president of the Geochemical Society, so my colleague in our sister society, she has served in many key roles, including chair of the Organic Geochemistry Division, founding chair of the Society's Ethics Committee, and she also contributes to several panels that coordinate international research efforts into climate research focusing on the Southern Oceans. Her scientific achievements have been widely recognized. She most recently received the Research Medal for Excellence in Antarctic Research from the Scientific Committee on Antarctic Research. So please join me in welcoming Elisabeth Liz Sikes.
Good morning. Thank you all for being here. It's early in the week. As Dan said, I've been looking at the Southern Ocean's role in climate change for many years. And the Southern Ocean's role in major climate change rests with the sequestration and release of CO2 from the deep ocean on glacial-interglacial timescales, particularly in the Lake Quaternary. I'm showing here one of the most influential records of paleoclimate from the last 20 years. This is the level of CO2 in the atmosphere, and as you can see here, it goes from about 180 parts per million in the last glacial maximum, which is the 20,000 years ago, to about 280. That's pre-industrial. We're at 400 now, 400 plus. But it comes out of the ocean very rapidly and in stages. And so this record, this high resolution record of CO2 was a real eye-opener because, well, all of the scientists of the 1980s looked at that and said, it has to have come out of a rapidly exchanged reservoir. And so the pace of that increase, 100 per parts per million in less than 5,000 years means it cannot be coming out of a slow exchanged reservoir. So we know it had to have been coming out of the ocean if it was rising that quickly. How and where and why is something we've been chasing for nigh on to 40 years. So the central question or central message in my talk is the Southern Ocean's role. So the Southern Ocean is where the ocean exhales, is where the deep ocean exhales. It lets out its reserve of CO2. And so this talk is going to give you a tour of ocean circulation with an emphasis on enhanced sequestration of CO2 in the deep ocean in the ice ages, and evidence for where that CO2 comes back out, and a little bit of nuance about release, timing of the release, and the ventilation, or what we call ventilation in the field, and the locale of the ventilation, because that's actually, those are the things that we have been focusing in on over the last decades since we've known that the CO2 changed by 1/3 in less than 5,000 years. So to look at this again, I can put some timing on this. There it is. So 20,000 years ago was the last glacial maximum. At 10,000 years ago, we were in the Holocene, so we had reached modern climate levels. And it really came out in two phases. The first phase during Heinrich I, and a pause in the Antarctic cold reversal, and another quick rise in the Younger Dryas. So memorize those time scales, because I'm going to repeat them a lot. Okay, so how does the ocean sequester CO2? Well, it relies on the global ocean circulation conveyor belt. This is the figure I use in my intro to oceanography classes, and it's a nice summary. So there's a warm surface current that runs up the Atlantic, known as the Gulf Stream, and it gets to the North Atlantic where the cold winds blow down, the Arctic winds blow down from the Canadian continent, quick chill that water. And it sinks because it's salty from having traveled at the surface and had the Saharan winds blow across it, and it sinks. And it begins this journey down the Atlantic to the Southern Ocean, where it re-exchanges, as I've already said. And the problem is this conveyor belt image, and like I said, this is what I use in my Intro to Oceanography class, because it's really easy to understand. It's really easy to see. But we really do need to stop thinking about the world. And this was coined by Wally Broker, and I give him a lot of credit for making this famous. But we've got to stop thinking about the ocean like Wally Broker and start thinking about it like Lynn Talley. It's really a 3-layer ocean, and that is how it holds its CO2. So the first thing is that the surface ocean, or above the thermocline, is a cap. So it's same idea. It comes up here, it quick chills, it flows down the Atlantic, called Atlantic Meridional Overturning Circulation, and it joins the Southern Ocean here, and it goes around the Southern Ocean, and then it has a deep arm which moves into that's the Pacific, and the Indian Ocean, which also sequesters CO2. So North Atlantic deep water becomes Antarctic bottom water in the Southern Ocean. And it is the recirculation of that Antarctic bottom water as Indian Ocean deep water and Pacific Ocean deep water that feeds the shallow layers. So if we go back to the North Atlantic where it all starts, you can look at this transformation of these waters at the surface. So here comes the North Atlantic current, Gulf Stream, whatever, and it actually goes into the Arctic. And so some of it goes very far north, some of it goes not as far north, and that sets up different densities. So salinity and temperature set up the density. So if we look at this in a cross section rather than a map view, so basically we're standing on North America and we're looking towards Europe, and so what we're looking at is this warm water coming north, and some of it goes very far north, as I just showed you, and becomes very cold. It does not get fresher, so it between the cold and the salt, it sinks to the bottom. That's the densest water. And those are Nordic Sea's overflow water. There's many names, and Denmark Strait overflows. Those are the densest water in the ocean. They sink down to about 3,000 meters and start traveling down the Atlantic. There's also, oh, sorry, that's not the button. Labrador seawater, which doesn't get as dense, and it fills the middle of the ocean as upper North Atlantic deep water. And so you begin to see that it's really important on how these things, how the ocean holds CO2, is that there's more than one layer, more than one shallow and deep layer. And so, and so if we look at this in a plane view of the global ocean, so we have 3 oceans here. We have the Atlantic. So here we are, starting in the North Atlantic, and there's the Pacific and the Indian. And so what it is the water starting in the North Atlantic is very dense. It's very salty. And it sinks to about 3,000 meters. It travels down the Atlantic, and it gets to the Southern Ocean where it rises back to the surface, because the Southern Ocean has very cold, dense water too. And so water will find its level based on density. And so what I want to point out here is this is this very salty water traveling down the Atlantic and getting to the Southern Ocean. And it travels around Antarctica in the Antarctic circumpolar current, which is how it recirculates and comes to the surface. And depending on where it does, it gets less dense or more dense. And so one of the important things about this journey in terms of chemistry is as it's traveling from the North Atlantic to the Southern Ocean, photosynthesis is going on above it. And so photosynthesis takes CO2 up from the atmosphere and it turns it into organic matter and shifts it to the deep ocean. So when we get to the Southern Ocean, we talk about the wind-driven upwelling there ventilating the deep ocean because it brings this CO2-rich water to the surface. And so what's been happening on that journey, as I said, the biological pump. So as we call it in oceanography. And what that simply is photosynthesis turns CO2 into organic matter, solid. It sinks. As it sinks, it gets respired because the ocean is oxic, so there's life going on down there. And out of the photic zone, you can only have respiration. So that, and red is inorganic and green is organic. So that water, that CO2 gets converted into organic matter, and then as it travels down the Atlantic Ocean, it gets respired back to CO2. And so they take up CO2, transform it to organic matter, respired CO2 dissolves in seawater as DIC. And I'll come back to the chemistry of that in a couple of slides, because CO2 makes organic matter, but organic matter in the ocean does not make just CO2. And so when this comes back to the surface, that dissolved inorganic carbon is in excess. And so it degasses to the atmosphere, and two shallow water masses, which are really important, Antarctic intermediate water, subantarctic mode water and Antarctic intermediate water, keeps the respired CO2 near to the surface. Because one thing that I think is an important misconception is you don't upwell 5,000 meter deep water to the surface. That's a really heavy lift. And so the stuff that does most of the work is the intermediate waters that sit between 500 and 1,000 meters. Oh, and yeah, and that water moves north or moves back underneath the ocean to the north. And so dissolved inorganic carbon, so CO2 is what plants, phytoplankton, use to make organic matter. But as soon as that is respired into the ocean, it interacts with the water. So CO2 is a very good weak acid, and so it becomes bicarbonate and carbonate. And so now these are species that are not in equilibrium with the atmosphere. I can show it better this way in a Bjerrum plot. So at the pH of the ocean, most of the CO2 is not CO2, it's bicarbonate, and it's not going to degas when it comes to the surface. It has to become CO2 to degas, and the same thing with carbonate. And so that at the pH of the ocean, we're mostly bicarbonate, and it's all in a mix between the carbonate species. And so, yeah, and it's controlled by pH. And the pH of the ocean is very set at around 8. It goes down to 7 point whatever and 8.1, but it's a salty soup, and it's very well buffered, and so it doesn't change its pH willingly. Okay, so if we want to look at this in another perspective, so I've just said photosynthesis takes up CO2 from the surface ocean, turns it into solid, and sinks it. That is perhaps the most important reaction, and it's the quick one. But there is also, and this is just another way of looking at it, but there is also calcification. And so calcium interacts with bicarbonate because it's what's there is the most of, and becomes calcium carbonate. Now there's a lot of organisms in the ocean that calcify, and they calcify and they take up that CO2, if you will, the DIC, dissolved inorganic carbon species. And the difference in the carbonate reaction is that there is actually a change in alkalinity, or that's what oceanographers use for balance of charges. So And these reactions, these reactions predominantly happen in the surface ocean, which is why I've just put a wonderful picture of a coral reef. So there's two arms of this carbon cycle in the ocean. If you're a land geologist or if you work on land, there's only photosynthesis. There really is very little calcification. But in the ocean, that's a pretty dominant reaction, or it's a pretty important reaction. So if we look at this a little bit differently with looking at the surface ocean's importance in this, what we have is that basically both of these reactions mostly happen in the surface ocean, photosynthesis and calcification. And once you get those products, those solid products into the deep ocean or into the ocean, that's usually in the deep ocean. And so really you can reverse photosynthesis with respiration, and you can reverse calcification with dissolution, but those reactions are not necessarily favored in the surface ocean. And so the point I'm trying to get to here is that these reactions are very common, both that and the reverse, but in the deep ocean, we have a lid on the soda bottle. So I'm going to show you this rather busy diagram, but what it is that thermocline really prevents these dissolved species from just coming back out of the ocean, because it really is like the cap on the soda bottle. And so if we want to look at equilibrium between the atmosphere and the ocean, then we have to look at equilibrium between the surface ocean, about 750 gigatons. Sorry, that's the atmosphere. And the surface ocean, it's a little bit more. So what it is because of these several species, the surface ocean holds a heavier load or a larger load of dissolved inorganic carbon than the atmosphere when it's in equilibrium. So we already have more CO2 or some CO2 in the surface ocean in equilibrium. But that biological pump that sinks that carbon into the deep ocean, where it returns to dissolved inorganic carbon, is really effective. That's why it's called the biological pump. So there's 50 times more CO2 in the deep ocean than there is in the surface ocean, and that is way more than would be in equilibrium if it was a homogeneous ocean. So, yeah, oops, there. So this then allows me to expand my schematic of how the Southern Ocean ventilates with, because it does, in a sense it does. It comes to the surface. It can just degas. That is how it gets back into the atmosphere. But it also impacts C13. So now we have a tracer. So now I can talk to you about paleoceanography. So when the phytoplankton take up CO2 to make organic matter, they discriminate by 20 to 25 per mil. So that means that the CO2 that comes back from the organic matter is depleted in C13, and we can trace that increase down the ocean and in the past, and then focus on where did that CO2 come from and go to. Yep, respired CO2 has a really depleted signal. And so when it's upwelled and degasses, and gets entrained in these shallow water masses, we then have a ready reservoir near the surface, not at 5,000 meters, that can exchange back to the atmosphere rather quickly if we can get it to upwell. So, how does it degas? The Southern Ocean is a windy place. And there's a lot of exchange. So this is just, I show this picture because you can see that spray. Every bubble of water that has more CO2 than the atmosphere can degas. And that's just a clear day wind. It gets pretty rough out there. So we should see this evidence of ventilated signal in shallow waters that's taking the cork, when they take the cork out of the bottle. So here's a bit more of a schematic where you can see this. So this deep water, upwells, yeah, but really it's these layers that are near the surface that come up and degas their CO2. They can also degas while they're traveling north. This is an upwelling zone in the Southern Ocean. And the water, there is water at the surface that's enhanced buoyancy. It doesn't hold a really large load, but they exchange right here. And so they interact, and so that deep water, interacts with the shallow water, it changes buoyancy and exchanges the CO2. I think that's what I wanted to say. Oh, okay, so let's go back to the easy conveyor belt, okay? And we can look at, because that gives us where we want to be, and we can look at 2 depth transects. One from way down the conveyor belt over here, that's the Pacific, that's the end of the conveyor belt. That's where as much CO2 as possible is in the deep ocean. And here at the bottom of the Atlantic, where it's only just traveled the Atlantic. And we can compare those. And with C13 as our marker, so here you have more CO2, it's lighter, it's more depleted because of that input of organic matter, and here is the CO2 that is less ventilated, or more ventilated because it's atmospheric CO2. So if you just look here at 3,000 meters, which is where the North Atlantic deep water sinks to, you can see this very large difference between the Southwest Pacific and Southeast Atlantic. And that is a measure of the ventilation, of how much respired CO2 has gone in. It's not it's a qualitative tracer for CO2, respired CO2 in the deep ocean. And so that's really important. So it's at 3,000 meters today. And, oops, that's the intermediate waters up there that I told you about. And see how they're the same in both oceans because they go around in the Antarctic circumpolar current and pick up and intermix their loads. And so here is a profile of the C13 in the last glacial maximum. And you can see, first thing I want to point out is that this low CO2, or this not respired low, is a lot shallower. And that's the mark of that water coming down the Atlantic. It hasn't been down there very long. It hasn't picked up a lot of respired CO2. So its signal is really enriched. And here at the bottom, the 2 oceans are not the same because they don't talk to each other. Why don't they talk to each other in the last glacial maximum? I'm an oceanographer, I can tell you. So, the special circumstance of Drake Passage, as we like to say, is the fact that it is the one place in the ocean where, Drake Passage allows the transport of water all the way around the planet, okay? So, all the way around the planet. So this is a continuous current, it's a global current, and so this water doesn't have to sink anywhere. It doesn't bump into a continent and downwell or upwell. But that's the Southern Ocean circulation today. And so when North Atlantic deep water comes down at 3,000 meters, it can enter the Southern Ocean. And it can enter the Southern Ocean because it's at 3,000 meters. Where did that go? There. And the thing is you can't cross the circumpolar current without some assistance. And so I'll put it as the physical oceanographers put it. A net meridional geostrophic transport cannot be supported in the absence of a net east-west circumpolar pressure gradient. And that's what happens above the sill depth in Drake Passage. So let's have a look at that. Oh, and so this water can enter the Southern Ocean and contribute to the formation of deeper waters like North Atlantic. So North Atlantic deep water contributes to circumpolar deep water. And so let's look at that in the Drake Passage. So Drake Passage has a sill, 2,500 meters. Funny that North Atlantic deep water the main tongue of North Atlantic deep water sits at 3,000 meters below the sill. So today the ACC goes through the sill. There are many sills, but they're all about the same place. And so it's easier to visualize it as Drake Passage because it's narrower. So North Atlantic deep water enters the Southern Ocean underneath the sill, gets into the Southern Ocean, and contributes to all the water masses that could go north. And anything shallower than the sill has to join the ACC and can't cross it. So let's look at the North Atlantic today. This is just a section of C13 in the ocean water, and you can see that there's the bolus. And yes, it gets lighter as it goes because it's getting respired into, but that's that bolus or that bulge of C13 enriched DIC. And if we look at, this is a compilation by Bill Curry and Delia Opa that came out 20 years ago, and you can see same picture, same colors, but you can see that there's the tongue. And so in the last ice age, glacial North Atlantic water became glacial North Atlantic intermediate water. So if we look at if I do my schematic for the last glacial maximum, this water can't have entered in the Southern Ocean. And I'm actually showing you here, that's the Weddell Sea, an important place for Antarctic bottom water to form. So that means that this water has to have come down and turned into the current and joined it without crossing into the deep basins of the Southern Ocean. And so what was the important contributor to North Atlantic deep water was probably different in the different basins. Okay, so without that input, let's look at the two oceans. So without the North Atlantic deep water input homogenizing the Southern Ocean, let's look at some cores we took off of New Zealand and some cores that Dave Lund took off of Brazil. Okay, and to put these in context, I want to make sure everyone's got let's just put some common vocabulary on this. So, last ice age, here, CO2 starts to go up in the Heinrich stadial, and there is, that reminds me, right. So this is a tracer for Atlantic meridional overturning circulation. So lower protactinium thorium, we have a slower current. And you can see here that just as the CO2 starts to rise, we're slowing that deep current down. Because, I mean, most people would think that you just push the CO2 out and into the Southern Ocean and it upwells and it degasses. But we see a slowdown in that current right when things start happening. So that's the end of the glaciation. That's halfway through Heinrich stadial. That's at the end of the Heinrich stadial. And this is a better picture of the upwelling. So this is a marker, this is a seminal paper by Bob Anderson from 2009. But you see, this is the signal of upwelling. It's just how much opal flux there was. So, and there's that halfway through the Heinrich Stadial event that I just showed you. And we took cores from off of New Zealand, and the way you do this is you go and get a bunch of cores that are at different depths, and you hope that they're all good, and then you can use them for oceanography. And we managed to pull that off a few years ago. And what's on here, in case you want to know what's on, this is the transect. That's the oceanography, the salinity. So, changes in ocean circulation and winds should change the C13 signal in subthermocline water. So let's look at that. So this study, this is the New Zealand transect, and so you can see the blue colors, the deep blue colors are depleted C13, and so that's our marker for increased CO2. What's also should be obvious is that the intermediate waters, which are here at about 1,000 meters, are ventilated today, but they weren't in the past. So there's a much shallower skin on the ocean that are ventilated skin, and so that's the CO2. That's that's the state of the ocean until the start of the deglaciation. This is a time of deep ventilation in Heinrich Stadial 1 that ended at about 16,000 years ago. Oh, started at 18, ended at 16, and so here we can see that after that point, which is the start of the Younger Dryas, it pulsed out. So there was a couple of steps that got us to the point where we could ventilate the entire deep ocean. It's really different in the Atlantic. So you can see here, same colors for the amount of CO2, and so this is today. Yeah, we're walking forward from the ice age to today, and you can see that the surface ocean is very ventilated, and there's your North Atlantic deep water with a low respired CO2 load. And so in the last ice age, it's shallower, and it's not carrying as much CO2. There's a pause, and then the CO2 blows out of the ocean, if you will. So here, at 14,000 years ago or so, is where you see that start. And here in the middle, you have this high CO2 load. All right, let me put that together. Okay, so here's our CO2 in the atmosphere coming out. There's the signal for the Atlantic meridional overturning circulation. So this is current speed, if I may. And so this shows you that there wasn't really a lot of flow enabling this release of CO2 from the deep ocean. In fact, this is upwelling intensity in the Southern Ocean. And you can see here that that upwelling intensity is directly related to these two phases of CO2 increase. And here, so what was the role of the Southern Ocean? Well, clearly it was upwelling like crazy and degassing, but it was also warming early. And so here are the records of sea surface temperature from a couple of different authors, and you can see that warming in the Southern Ocean began quite early, about 20,000 years ago. And that's where we start. That's where I'm going to start with making the case for the Southern Ocean's importance. So, if meridional overturning circulation was not driving CO2 release, so it's not like someone took the bus and shoved them out the door, but what are the other mechanisms? Well, first, early mid-latitude, so warming, gas likes to be in cold water. So first we're warming the planet around the Southern Ocean. So the Southern Hemisphere was warming. And then I can show you evidence for early oxygenation or CO2 release from the Southern Ocean. So you're warming it, you're opening those fronts, and you're kicking the CO2 out. So southward frontal movements shifts during the deglaciation. So really, the ocean warmed, and then by warming, the fronts moved south. The winds in the fronts moved closer to Antarctica. And this is a really lovely study from a couple years ago where they showed that the locus of the fronts was 6 degrees latitude closer to the equator than today. And so that is the, so as the fronts moved south, where you could get the wind to blow across them, and I keep showing you those pictures of the Southern Ocean with those white caps, so that will help it out. Oops, there we go. And so this is where the fronts sit today. There are 3 important fronts. Each of them has air-sea exchange at the front where water goes down. But this is just showing you a paper from Karen Kofeld from a few years ago that shows how far the fronts moved. And so this is, we've been building up evidence. So the fronts did move. They moved to a different location where they were more effective at letting CO2 out. And I showed you that picture from Steve Rintoul where you can see that escape hatch. And so our location lately has been the Indian Ocean, and that front sits right here. Oops, right here. And mode water is that shallow water that moves north just below the surface. And the upwelled or upper circumpolar deep water, so the water that's holding the CO2, comes up. It doesn't really get to the surface, but it talks to the mode water, and they exchange intel. Okay, so this is another paper that shows where the ventilation hotspots are. So these red dots are just parcels of water that rose up from the deep ocean. And so here we have the parcels that have risen from 1,000 meters, but here this is 200 meters crossing. So you can see here, and it's topography. Another important piece is topography. So these dark shadows are undersea, I'm looking for the word for shallow places. Anyway, bumps. And so when you run into the Kerguelen Plateau, the Campbell Plateau, you get squeezed at Drake Passage, and the Crozet Plateau, you degas. So these are the places where the degassing is happening. And so if we just schematic it, okay? What you can see here is the subtropical front, which is the northern rim of the Southern Ocean, sits here today. And see, there's all this space between here and Australia, but it's kind of up against New Zealand already. And so you can move the fronts north in the deglaciation in most places in the ocean, except for south of Australia and south of New Zealand. And what's interesting is, not interesting, but was another important paper that came out a couple years ago showed that this, there was a switch. So this is the East Australia Current, which just delivers water to the Southern Ocean, warm water to the Southern Ocean, and in the last glacial maximum, it shifted. And so there's another escape place for the CO2. And so the westerly wind system and the southern tropical front shifted more north in the last ice age, and as it shifted south, it let the CO2 back out. So this is where our study was in the Indian Ocean. So I'll show you some real paleoceanographic data. So this is high salinity. My student, Ryan Glaubke, ran the trace elements and calculated the salinity, and you can see that the deep water that came up was very salty. The other thing, going back to radiocarbon, or bringing up radiocarbon, is my postdoc Natalie Umling ran the C14 on planktonic foramps. And so the thing about that is C14 isn't a chronometer. And so here you can see as that deep salty water came up, it brought with it very old CO2, up to 6,000 years. And I show here for backup this paper from the northern Indian Ocean, because when we sent this out to review, the reaction was, that's really old. Is that possible? And I'm like, well, these guys published the same thing a couple years ago. So there's evidence for it from many places in the Indian Ocean. But this really old water came up just as these fronts began to move. So that shows that the ocean, that the fronts basically let the CO2 out when the winds and the fronts were in the right place for a lot of degassing. Yeah, okay, so there, okay? And you don't just have to have it from the deep ocean. You can have it from the near surface. And so the fact that this water stays at the surface for a long distance is also important. So let's look at the evidence for oxygenation. So CO2, AABW forms in several locations, and they were different in the last ice age because it wasn't a homogeneous Southern Ocean. So I'll show you three different locations, but I want to start with the Atlantic because it is so different. So, bottom water oxygen, okay. Respiration takes oxygen and gives off CO2. So now we're looking at the other thing. As we lose oxygen, we're enhancing respiration. And so this is from the Southern Indian Ocean, published in 2016. And this is the uranium. And so uranium is soluble in dysoxic water. So when you blow that CO2, when you increase the ventilation of the deep ocean, you precipitate uranium. And so this is the signal of the uranium that was in dissolution, but it's not anymore because we oxygenated it. And you can see that that occurs between 13 and 10,000 years. That's really late, okay? The CO2 most of the CO2 was out of the ocean by then. So what's up with that? So the Atlantic was really late to the party, and that's where the water comes out of the Atlantic, right? North Atlantic or Atlantic meridional overturning circulation. So this top record, oh, okay, yeah. So earlier than this, the Pacific started, this is the same, this is the gray part is the Heinrich, the Heinrich stadial, and it is the beginning of the deglaciation. So in the Pacific, it was oxygenating before the deglaciation. These in the middle are mostly our work. They show that oxygenation was occurring contemporaneous with deglaciation, and there's the Atlantic where it's later than deglaciation. And for those of you who do uranium or do, basically that's an 8,000 year lag, and so it can't just be a sedimentation problem. So I know it's a little bit more subtle than it's going to happen at the same time. So my overarching theory for this is, I told you that the sea surface temperature warmed up really early. So if you melt back the ice, you can allow the water, the CO2, the water to rise to the surface and interact with the atmosphere. So starting in different times, in different places, the sea ice melted back. It allows your upper circumpolar deeper and lower circumpolar polar deep water to degas, and you don't need your North Atlantic deep water to do that, like you did in the Atlantic. So, and it brings me back to the nuances of CO2 chemistry in the ocean. It doesn't just come back as CO2, okay? It's already spent 20,000 years in the deep ocean becoming different species. And so when it exits, it's going to exit slowly. It took 5,000 years to get back out. It probably went around a couple times in this loop. So, to summarize, early Southern Ocean warming and ice loss allowed ventilation. The Southern Ocean was covered with ice in the glaciation a lot farther out than it is now. And so the wind shifts and frontal positions, the fact that they track CO2 increase tells us that they are critical to letting the CO2 out of the ocean. And these Southern Ocean drivers occurred long before meridional overturning circulation in the Atlantic reinitiated. So my conclusion, if you will, is that physical processes in the Southern Ocean appear to have been really important in getting the CO2 out of back into the atmosphere. And I think with that, I'm going to leave you with, the Southern Ocean. It's degassing all the time. Thanks for your attention. Six minutes over. 6 minutes over. I'm going to sit down.
Okay, then you should take this, yeah? Mm-hmm. Yeah, thanks, Liz, for this wonderful talk. We have some time for some questions. If people would like to come to the microphones are in, it's actually hard for me to see. But if people would like to pose a question, then
You may.
Then it's possible.
Please do.
While people, oh yeah, please. No, that microphone doesn't seem to be on. Maybe there's a switch on it or something, or maybe someone can.
Well, I could probably talking very loudly. The question was, what is your opinion about the balance of the processes you described in your talk and other things that might have been going on at the land surface or in the shallow oceans that would affect the carbon cycle? For example, as the seas rise and vegetation then breaks down in the newly flooded regions. I'm sure we could brainstorm any number of other land surface processes that would be occurring because of the change.
Okay, there definitely was uptake of CO2. There is uptake of CO2 by land plants. And so that is actually a substantial or a reasonable amount. But I don't have those numbers in my head. I think they're like 30%. But the rapidity of that exchange is what puts the ocean signal on it, or puts the imprint of the ocean on it, at least substantially. How's that? I'll be non-quantitative.
Okay, is there a question over there? I hope the microphone's on now.
Yeah, sounds like it.
Yeah.
Yeah. Hi, thanks for that talk. You talked about how important it is to really understand these ventilation patterns, right? That this intermediate path is kind of the contribution to. So my question is, do we further understand these ventilation patterns to get a clearer picture of CO2 output from the Southern Ocean? Or is that already understood to the degree that we can make these kind of broad assumptions?
Are you asking what percentage came out of the Southern Ocean?
No, if the ventilation patterns in the Southern Ocean are well enough understood to really come up with these kind of exact date and kind of CO2 room.
Well, I leave that to the physical oceanographers, but I will say that the physical oceanography, so that's the modern circulation people. They have been studying this really carefully because of the interaction of the ocean and the atmosphere and anthropogenic CO2. So yeah, it's pretty well understood. I don't have those numbers in my head, but certainly like for example, there was a study that came out, let's say a year or two ago, that showed as the fronts have been moving south in the Southern Ocean now because of the warming, the interactions have been changing. So it's more effective. Yeah, when they're in the right place, they're really effective, the fronts. Does that answer your question?
Kind of.
Okay.
But I will come to you later.
Okay, yeah.
So, are there any other questions? I mean, this is very far from my field, but I have a burning question. It's probably very naive, and I'm sure everybody else would know the answer to it. But at some point during your talk, you put on a diagram, and it showed the carbon-13 levels through the ocean in the past. So how do you obtain that data? That seems fascinating to me. You know,
So I showed that cross-section with the cores going down. So each core is at a different depth, and then we just go back in time in that core and measure the isotopes.
But the isotopes showed a profile through the ocean, did they not?
Yeah. So one of those points was from one core. One of those points was from a deeper core. Another point was from a deeper core, and then yet a deeper core.
Okay, yeah, but it's like through the ocean column, and that sort of settles in the core so that it's still sort of.
Well, things settle below the surface. I can here. This is great. I can show this.
Thanks for explaining this to me.
I actually put that in there. Oh, it's really at the beginning. Oh, well, it's okay. Here, so each of these points, each of those, that's a core that was taken at 500 meters, and then we just counted down the core back in time, because the core has a certain amount of time in it. And so we picked, and then we dated it and stuff. But so each one of those horizontal lines of dots, that's a core.
Okay, yeah, now I start to.
And then we counted back through the core. So I can go back. There it is. So those are the cores. That's where they sit. And then each one of those cores has a certain amount of time.
I see.
So yeah, I mean, it takes a couple of years.
Okay.
It's a slow process, because actually one of the things that I've done to myself is that these are multi-core studies, and what you should do is publish each core as it comes out and say, oh, well, I showed this with this core, but we waited and did it all at once. But no, it's a painstaking process.
Right. Let's thank Liz once more for this wonderful talk. Thanks very much.